Welcome back, everyone. In part 1, we saw how post-tensioning gives concrete muscles. Think of it like holding a stack of books horizontally. If you don't squeeze them hard enough from both ends, they'll fall. That squeeze is our active force, unlike regular reinforced concrete, which waits for a load to start working. Post-tension slabs are pre-compressed, ready to fight gravity from day one. Today, we'll look at the math that keeps these muscles strong and how the ASCII 318 code ensures they don't overexert themselves. Let's talk about the magic formula. To find the stress at any point, we use the combined stress equation. Stress equals P over A plus or minus M times C over I. The P over A part is the uniform squeeze we just talked about. The M times C over I comes from the bending moment. But here's the trick. In PT slabs, we have an eccentric force because the tendon isn't in the middle. This creates an internal moment that actually counteracts the external loads. It's like leaning back while carrying a heavy box to stay balanced. Now we don't get all the force we pump in. Some is lost immediately. First, there's friction. Imagine pulling a rope through a curved garden hose. The more curves and the rougher the hose, the harder it is to pull. In PT, the steel rubs against the duct. We also have elastic shortening. As we squeeze the concrete, it shrinks slightly like a spring, which causes the steel to slacken just a tiny bit. We must account for these thefts of force during the design stage. Then there are the long-term slow losses. Concrete is alive in a way. It changes over time. Shrinkage happens as water evaporates and the slab physically gets smaller. Then there's creep. If you stand on a memory foam mattress, you sink slowly over time. Concrete does the same under constant pressure. Finally, steel relaxation happens when the high-strength wires get tired of being stretched and lose some tension. Total losses can range from 15% to 25%, so we always over-tension at the start to compensate. In continuous slabs with multiple spans, things get spicy. When we tension a tendon, the slab wants to lift up, but the internal supports, columns say, "No, you stay here." This restraint creates secondary moments. Think of a group of people holding hands in a line. If one person jumps, the others feel a tug. These moments are hyperstatic, meaning they are caused by the structure's own constraints. We must add these to our primary moments to get the total design effect. The ASCII 318 code is our rulebook. It checks the slab at two critical life stages. First is the transfer stage. This is right after we jack the tendons. The concrete is still young and hasn't reached full strength, but it's being hit with the maximum press force. The code limits the compression to 0.6 of the initial concrete strength, FCI, to prevent crushing, and limits tension to prevent cracking before the building is even finished. Next is the service stage. Now the building is occupied, full of people and furniture. The concrete is at full strength, but the press force has dropped due to those losses we discussed. ASCII 318 categorizes slabs here. Class U, uncracked; Class T, transition; and Class C, cracked. Most PT slabs are designed as Class U, meaning we keep the tension so low that the concrete theoretically never cracks under normal loads. This is why PT floors look so smooth and perfect. One of the coolest ways to design PT is load balancing. Since the tendon is a parabola, it exerts a constant upward pressure. We can choose a tendon force that exactly cancels out a percentage of the dead load. It's like the slab is floating. If we balance 80% of the weight, the slab only feels 20% of its own gravity. This allows for incredibly long spans and very thin slabs that would be impossible with traditional rebar alone. So, to recap, we use the combined stress formula, account for immediate and long-term losses, and handle secondary moments in continuous spans. We always stay within ASCII 318 limits to ensure safety at both transfer and service stages. Post-tensioning isn't just about strength. It's about control, controlling cracks, controlling deflections, and pushing the boundaries of what concrete can do. Thanks for joining me at Strong Foundation Engineering. Subscribe to keep building smart.